I can turn this paper from a floppy sheet into a rigid structure, strong enough to support the weight of another object. Well, I can't, but people can. All you have to do is fold the paper in a particular way, and now we've got all these structures that can move and bend and behave in unique ways. And that's because when we fold paper, we're not just changing its shape, we're changing its physical properties. Origami is probably the world's most famous example of the shape-shifting power of paper. It's an ancient Japanese art form of turning flat paper into intricate sculptures through a series of folds. And for hundreds or even over 1,000 years, we've been using origami to make art and decorations, to introduce geometry to elementary students, design buildings, and even solve major physics riddles. How? Well, paper is a material that can behave differently because of changes in its structure, even when the material itself doesn't change. It's what's known as a mechanical metamaterial. In other words, these flat and creased pieces of paper are made of exactly the same thing. But the creased paper is stronger because of the structure of its folds. And when we stack folds in a systematic way, suddenly we've changed the paper's size, flexibility, and rigidity. Let's take a closer look. This one is called the water bomb, or balloon pattern. Traditionally, it was used for making toys and boxes for trapping insects. It can pucker closed or stretch open, giving it a lot of flexibility. And once all the folds are complete, you have a flat shape. But you can inflate it with air or even fill it with water to expand it into a 3D object. And this one is the Yoshimura pattern. It actually forms naturally when a cylinder is compressed from the ends. It also happens when you push up your sleeve. But when we make it from a flat sheet of paper, the pattern can fold flat. Then when it expands, it forms a strong cylinder that can hold up to compression. And that's because the force of the compression is distributed evenly among these triangular structures, and there are no weak points that will collapse. This last one is called the Miura fold. It's made of these zigzagging folds that create a tessellated or repeating pattern of parallelograms. Each section of this pattern stays flat. There's no dimpling or bending to tuck one section inside of another. And it's special because for most materials, like this piece of balloon, if you stretch it in one direction, it shrinks in the opposite direction. But with the Miura fold, expanding it in one direction also makes it expand in the other. Materials with this property are called auxetic, and they're really good for absorbing energy and resisting damage from impact. But origami isn't just for paper. Another way to think of it is that the folds are like hinges that connect the flat parts of the paper, which are called panels. So we can replace the origami hinges with mechanical ones, and the panels can be made of metal or plastic or glass, and that opens up all kinds of other ways to use origami. Like in 2006, a team of researchers worked with the water bomb pattern to make the first origami-inspired medical stent. It's a small metal device that's inserted into an artery or vein to keep it open. With its origami design, the device can fold up small, then unfold and expand once it's in place in the body. The strength of the Yoshimura pattern has applications in architecture and building things like pop-up shelters from wood and cardboard. And the Miura pattern can be used for making things like deployable bridges or solar panels that need to be compact for storage or transportation. And we're still exploring new patterns and applications for origami. Like these patterns all use triangles or parallelograms, but researchers are exploring new types of panels and folds. In 2025, researchers even discovered a whole new class of folds that have been named bloom patterns. The bloom pattern folds entirely flat into a compact circular column. Then with a slight tug, it can expand into a bowl shape or even a large flat disc. These patterns can be useful for everything, from making pop-up bowls that store flat in your kitchen cabinets, to storing and transporting space telescopes. Physicists have also started modeling trapezoid panels. That might not sound like much, but it's actually a really big deal. Trapezoid origami has a unique way of expanding and contracting in even predictable patterns called breathing, or twisting into a helix called shearing. And that could open up new ways to combine folds and design objects that are particularly good for absorbing energy and impact. Origami can have curved folds too. Curved crease origami is difficult to build and even harder to describe mathematically. But in 2012, physicists finally came up with an equation to describe origami curves. It's an entirely different way to create 3D structures from 2D sheets. And when materials bend, they store potential energy. So curved structures may be able to unfold more easily and with less external guidance than other origami patterns. Plus, they have smooth, rounded sides that could be better for making medical devices that unfold inside the body without causing damage or irritation. And that's kind of wild. Think about it. For hundreds of years, we've been figuring out how to harness the power of art, geometry, and physics to make innovative, useful, and beautiful things. And we still don't have it all figured out yet. We're still finding new ways to fold paper, and that means the possibilities of origami are still wide open for us to explore.